What if I told you that right now, at this very moment, there's an object hurtling through our solar system that's breaking every rule we thought we understood about comets? I'm not talking about some minor anomaly that scientists can easily explain away. I'm talking about something so bizarre, so completely unprecedented, that astronomers are literally watching their models fail in real time. Comet C 2024 S1, better known as Atlas, was discovered on September 27, 2024, by the Atlas Survey in Hawaii. And here's where things get absolutely wild. This comet was supposed to survive its close encounter with the Sun. Every calculation, every model, every bit of computational power we threw at it said the same thing. But on October 28, 2024, something happened that has sent shockwaves through the astronomical community. Atlas didn't just disintegrate. It didn't just break apart. It vanished in a way that has some scientists questioning whether we actually understand comets at all. Here's the mind-blowing part that should make your jaw drop right now. Atlas was behaving normally, doing exactly what our centuries of comet observations predicted, right up until it wasn't, and the moment it stopped following the rules. That's when things got so strange that even veteran astronomers with decades of experience started using words like unprecedented and inexplicable. We're talking about scientists who have watched hundreds of comets, who can predict orbital mechanics with stunning accuracy, suddenly admitting they have no idea what they're looking at. But here's what will really keep you up at night. Atlas might not be an isolated incident. It might be the first domino. And if that's true, then everything we think we know about our solar system's stability, about Earth's safety, about the predictability of space itself, might need to be completely rewritten. This isn't just about one comet. This is potentially about discovering that the universe has been hiding a fundamental truth from us, and we're only now getting our first glimpse behind the curtain. Before we go any further, I need you to do something for me. Smash that like button right now, because this video took months of research to put together, and YouTube needs to know that deep scientific content matters to you. Hit subscribe and turn on notifications, because we're about to go on a journey that will fundamentally change how you see the night sky. And here's something I'm genuinely curious about. Drop a comment right now telling me what country you're watching from and what time it is where you are. I want to see how this story is reaching people across the planet, because what we're discussing today affects every single person on Earth, regardless of where you're standing. Now, let's start with what should be a simple question, but I promise you, by the end of this video, you'll realize it's anything but simple. What exactly is a comet? And more importantly, why should one comet acting strangely make any difference to your life? To understand why Atlas is so significant, we need to build a foundation. And I'm going to tell you something right now that might surprise you. Most people, even educated people, have a completely wrong mental model of what comets actually are. You probably picture them as these solid rocks of ice flying through space, right? Maybe you're imagining something like a giant snowball with a tail. That's what I thought for years. That's what most textbooks will tell you. But here's the first twist in our story. Comets aren't really solid at all. They're more like flying gravel piles held together by ice. Think of it like this. Imagine taking a bucket of gravel, pouring water over it, and freezing it solid. Now imagine throwing that frozen mess into space and heating it up. That's closer to what a comet actually is. Dr. Michael Ahern from the University of Maryland, who led the Deep Impact mission in 2005, discovered something remarkable when NASA literally crashed a probe into Comet Tempel 1. The comet wasn't solid ice. It was more like fluffy powder, with a density closer to quark than to rock. That single experiment changed everything we thought we knew about comet composition. But it gets even stranger. Comets are ancient. I'm not talking about old like the pyramids, or even old like the dinosaurs. I'm talking about objects that have existed virtually unchanged since the birth of the solar system itself, 4.6 billion years ago. Every comet is a time capsule, carrying pristine samples of the original material that formed the sun and planets. When you look at a comet, you're literally looking at the building blocks of worlds. Now here's where it starts to get really interesting. Comets come from two main regions in our solar system. The first is the Kuiper Belt, that ring of icy objects beyond Neptune's orbit where Pluto lives. Comets from this region are called short-period comets, and they orbit the sun in relatively predictable patterns, usually taking less than 200 years to complete one orbit. These are the comets we know well. We've studied them. We understand their behavior. They're predictable, reliable, almost boring in their consistency. But then there's the second source, and this is where things get mysterious. Way out beyond the Kuiper Belt, somewhere between 2,000 and 100,000 times the distance from Earth to the Sun, there exists a theoretical shell of countless icy objects called the Oort cloud. We've never actually seen the Oort cloud directly. We can't. It's too far away, too dark, too dispersed. We only know it exists because of the comets it sends our way. And the comets that come from the Oort cloud? They're the wild cards. They're the visitors from the deep freeze, objects that have spent billions of years in the coldest, darkest reaches of space, so far from the sun that they're essentially at the temperature of the cosmic microwave background itself. Think of it like this. Imagine you have an enormous freezer, but instead of being the size of your kitchen, it's bigger than our entire solar system. And in that freezer, you've stored billions of snowballs that have been there, completely unchanged, since before the Earth even existed. Every so often, something disturbs one of these snowballs. Maybe it's the gravitational pull of a passing star. Maybe it's the subtle tug of the Milky Way's galactic tide. Whatever the cause, one of these ancient objects gets knocked loose and begins a million-year journey toward the sun. That's an Oort cloud comet. And Atlas? Atlas is one of these visitors from the deep freeze. Dr. Jan Oort, the Dutch astronomer who first theorized this cloud's existence in 1950, made a brilliant deduction. He noticed that long-period comets, the ones that take thousands or even millions of years to orbit the sun, seemed to come from all directions equally. They didn't cluster in the plane where the planets orbit. They came from above, below, from every angle. The only way to explain this distribution was if there existed a spherical cloud of comets surrounding the entire solar system. He never saw it. He died in 1992 without direct confirmation of his theory. But every long-period comet that arrives from the depths of space is a testament to his genius. Now, here's what makes Oort cloud comets particularly special and particularly dangerous. They're coming in for the very first time. Unlike short-period comets that have made multiple passes around the sun, these first-time visitors are pristine. All their volatile materials, all their ices, all their frozen gases are intact. When they get close to the sun for the first time in their existence, they don't just warm up gradually. They explode with activity. They develop massive tails. They outgas furiously. They become some of the brightest and most spectacular objects in the night sky. But here's the catch, and this is crucial for understanding what happened with Atlas. All of this activity is also incredibly destructive. Remember, these comets aren't solid rocks. They're barely held together. And when you take something that's been frozen solid for billions of years and suddenly subject it to the intense heat and radiation of the sun, bad things can happen. The ice sublimes, turning directly from solid to gas. The comet starts spinning faster as it loses mass unevenly. Thermal stress creates cracks. And sometimes, catastrophically, the comet just falls apart completely. Comet disintegrations aren't exactly rare. In fact, Dr. Zdenek Sekanina from the Jet Propulsion Laboratory has documented hundreds of cases where comets broke apart as they approached the sun. In 2011, Comet Elenin disintegrated. In 2013, Comet Isan, which was supposed to be the comet of the century, broke apart just before reaching its closest point to the sun. In 2020, Comet Atlas, yes, a different Atlas comet designated C2019Y4, fragmented into dozens of pieces. So when astronomers first started tracking our current Atlas, C2024S1, they knew disintegration was always a possibility. But here's what's different, and this is where we start to move from known science into genuinely puzzling territory. The way Atlas disintegrated doesn't match any of the patterns we've seen before. And the timing? The timing makes absolutely no sense based on our current models. Let me explain why this is so strange. When comets break apart, they typically do so in one of several well-documented ways. Sometimes they split into a few large fragments that continue orbiting separately for a while before eventually disintegrating further. Sometimes they crumble gradually, leaving a trail of debris along their orbital path. Sometimes they experience a catastrophic fragmentation event where they explode into countless tiny pieces all at once. We have mathematical models for all of these scenarios. We can predict, based on a comet's size, composition, orbital path, and activity level, roughly when and how it might break apart. Atlas was tracked intensely from the moment of its discovery. The Atlas Survey, which stands for Asteroid Terrestrial Impact Last Alert System, is specifically designed to find potentially hazardous objects. It consists of 4 telescopes located in Hawaii and South Africa, and it scans the entire visible sky every 24 hours. When Atlas discovered this comet, astronomers immediately began calculating its orbit, and what they found was both exciting and concerning. The comet was on a trajectory that would bring it incredibly close to the Sun, reaching perihelion, its closest approach, at a distance of just 0.031 astronomical units. To put that in perspective, that's about 4.6 million kilometers, or roughly 13 times the distance from the Earth to the Moon. That might sound like a lot, but in astronomical terms, that's frighteningly close. The Sun's corona, its outer atmosphere, extends millions of kilometers into space. Atlas wasn't just getting close to the Sun. It was going to graze through the outer reaches of the Sun's atmosphere itself. This made Atlas what astronomers call a sun-grazing comet, and it placed it in a special category called the Kreutz group. The Kreutz sungrazers are a family of comets that all follow remarkably similar orbits, and there's a fascinating story here. These comets are all believed to be fragments of a single, enormous comet that broke apart centuries or perhaps millennia ago. Every time one of these fragments returns, it passes extremely close to the Sun, and many of them don't survive the encounter. The Solar and Heliospheric Observatory, or SOHO, has discovered over 4,000 sun-grazing comets since its launch in 1995, and the vast majority of them disintegrate completely as they round the Sun. So when Atlas was identified as a sun-grazers, astronomers knew it was in danger. But here's the thing. Atlas was big. Initial estimates put its nucleus at somewhere between 3 and 5 kilometers in diameter. That's massive for a comet nucleus. For comparison, the comet that killed the dinosaurs 66 million years ago was probably only about 10 kilometers across. A comet nucleus several kilometers wide has a lot of structural integrity. It has enough mass that gravity helps hold it together. It should be able to withstand significant thermal stress. Dr. Kwanzi Lee from the University of Maryland, one of the leading experts on comet fragmentation, was tracking Atlas closely. In late September and early October 2024, he and his colleagues were making regular observations, measuring the comet's brightness, analyzing its gas production, looking for any signs of distress. And according to their observations, Atlas was healthy. It was brightening as expected. Its coma, the cloud of gas and dust surrounding the nucleus, was developing normally. Everything looked good. But then something changed. And this is where our story takes a turn into genuinely mysterious territory. In the days leading up to October 28th, Atlas began to brighten more rapidly than expected. On the surface, this might seem like a good thing. A brightening comet is an active comet, releasing more gas and dust, becoming more spectacular. But to experienced comet observers, rapid brightening can also be a warning sign. It can indicate that the nucleus is fragmenting, exposing fresh ice to sunlight, causing a sudden outburst of activity. On October 28, 2024, multiple observers around the world reported that Atlas had suddenly become much fainter. Not gradually dimmer, as you might expect if it was just moving away or running out of volatile material. It dropped in brightness dramatically, almost overnight. When astronomers pointed their telescopes at where Atlas should be, they found something shocking. The comet was gone. Not disintegrated into a few large pieces that they could still track, not crumbled into a debris trail. Just gone. Where there should have been a bright, active comet nucleus, there was nothing but a faint, dispersed cloud of dust. Here's what makes this absolutely extraordinary. Atlas vanished while it was still relatively far from the Sun. It was still about 0.08 astronomical units away from perihelion, still about 12 million kilometers from its closest approach. At that distance, the solar heating, while intense, shouldn't have been enough to completely destroy a comet nucleus of Atlas's size. The thermal models, which have been refined over decades of comet observations, predicted that Atlas should have survived at least until it was much closer to the Sun. Some models suggested it would make it through perihelion entirely, emerging on the other side as a somewhat smaller but still intact nucleus. But Atlas didn't follow the models. It didn't even come close. And when scientists went back and analyzed their data, looking for clues they might have missed, they found something even more puzzling. There was no obvious trigger for the disintegration. There was no evidence of a major outburst in the days before the breakup. There was no impact from another object. There was no sudden change in the comet's rotation rate. One day, Atlas was there, behaving normally. The next day, it was effectively gone. Now, you might be thinking, okay, so a comet broke apart earlier than expected. That's unusual. Sure, but is it really that big a deal? Scientists are wrong sometimes. Models are just approximations. Maybe Atlas was more fragile than they thought. Maybe there was some hidden structural weakness. Maybe it's just a weird outlier, a statistical anomaly. And that's a perfectly reasonable response. That's exactly what some astronomers are saying. But here's where the black swan concept comes into play, and why a growing number of scientists are suggesting that Atlas might represent something far more significant than just one weird comet. The term black swan was popularized by Nassim Nicholas Taleb in his 2007 book, and it refers to an event that has three characteristics. It's extremely rare and unexpected. It has a massive impact, and people try to explain it after the fact as if it were predictable all along. The classic example is the 2008 financial crisis. Before it happened, most economists thought the financial system was stable and robust. When it collapsed, it caught almost everyone by surprise. And afterward, people looked back and said, "Oh, we should have seen this coming." The warning signs were all there. Black swan events are dangerous precisely because they reveal flaws in our understanding that we didn't know existed. They show us that our models, our theories, our carefully constructed frameworks for understanding the world have blind spots. And in those blind spots, catastrophe can hide. So the question we're really asking is this: is Atlas a black swan event for astronomy? Does its unexpected disintegration reveal a fundamental gap in our understanding of comets? And if so, what other surprises might be lurking in that gap? To answer that, we need to go deeper into the science of what actually holds a comet together and what makes it fall apart. And I'm going to warn you right now, what we're about to discuss is going to challenge some very basic assumptions you have about how solid objects behave in space. Because it turns out that comets don't follow the rules that apply to rocks or ice cubes or any of the solid objects you interact with in your daily life. Comets are weird, and the more we study them, the weirder they get. But before we dive into that, let me ask you something. How many of you have actually seen a comet with your own eyes? Not in a photo, not on TV, but actually gone outside and looked up at a real comet in the night sky? Drop a comment and let me know. Because I think one of the reasons people underestimate the significance of comets is that they seem so distant, so abstract. They're just points of light, if you can see them at all. But throughout human history, comets have been seen as omens, as harbingers of change. And maybe, just maybe, our ancestors understood something we've forgotten. That these visitors from the outer darkness are messengers, warning us that the universe is far more dangerous and unpredictable than we'd like to believe. Let's talk about comet fragmentation. And I mean really dive into the mechanics of what happens when a comet breaks apart. Because this is where things get genuinely fascinating and more than a little bit terrifying. First, forget everything you think you know about how objects break. If I hand you an ice cube and ask you to break it, you can do it easily, right? You can drop it on the floor. You can crush it in your hand. You can let it melt. The mechanics are simple and intuitive. You apply force. The molecular bonds holding the ice together fail, and the cube breaks into pieces. Simple cause and effect. But comets don't work that way. A comet nucleus exists in an environment so alien, so fundamentally different from anything on Earth, that our intuitions completely fail us. Think of it like this. You're in the vacuum of space. There's no air pressure, no friction, no atmosphere to slow you down or stabilize you. You're being heated on one side by the sun's radiation, while the other side of you remains at nearly absolute zero. Parts of you are sublimating directly from solid to gas, creating jets of material that push against you asymmetrically. You're spinning, possibly tumbling chaotically. And all of this is happening to a structure that's barely held together in the first place, that's riddled with cracks and voids, that's a mixture of ice and rock and organic compounds with different melting points and structural properties. This is the reality of a comet nucleus, and it explains why predicting comet behavior is so incredibly difficult. Dr. Naomi Samarasina from the FINDA Planetary Science Institute has spent decades studying comet rotation and fragmentation, and he's developed mathematical models that attempt to account for all these variables. But even with our most sophisticated models, comet behavior remains partially unpredictable. Because we're dealing with what mathematicians call a chaotic system, one where tiny differences in initial conditions can lead to wildly different outcomes. When a comet fragments, it typically happens through one of several mechanisms, and understanding these mechanisms is crucial for grasping why Atlas is so puzzling. A first mechanism is rotational breakup. As a comet gets closer to the sun, it outgases, releasing jets of vapor from its surface. These jets act like tiny rocket engines, and if they're asymmetrically distributed, they can cause the comet to spin faster and faster. Eventually, if the comet is spinning fast enough, centrifugal force can overcome the weak gravitational and structural forces holding the nucleus together, and it literally tears itself apart. This is what happened to Comet 73P Schwarzmann-Walkman 3, which broke into dozens of fragments during its 1995 approach to the Sun. The second mechanism is thermal stress. As the Sun heats the surface of a comet nucleus, the heat doesn't distribute evenly. One side might be in direct sunlight, while the other is in shadow. The temperature difference can be extreme, hundreds of degrees. This creates internal stresses as different parts of the comet expand and contract at different rates. If the comet has pre-existing cracks or weak points, these thermal stresses can cause it to split along those fracture lines. This is likely what happened to Comet LINEAR in 2000, which broke into at least a dozen pieces as it approached the Sun. The third mechanism is tidal disruption. When a comet gets very close to a massive body like the Sun or a planet, the gravitational force on the side nearest the massive body is stronger than on the far side. This difference in gravitational pull creates tidal forces that stretch the comet. If the comet gets close enough, these tidal forces can exceed the comet's structural strength, and it gets torn apart. This is what happened to comet Shoemaker-Levy 9 when it passed too close to Jupiter in 1992. The comet was ripped into at least 21 distinct fragments, which then all crashed into Jupiter 2 years later in one of the most spectacular astronomical events ever witnessed. Now, here's the critical question. Which of these mechanisms destroyed Atlas? And here's the deeply unsettling answer. We don't know. And what's more, none of them quite fit. Atlas wasn't spinning fast enough for rotational breakup. Observations of its brightness variations, which indicate how fast a comet is rotating, suggested a rotation period of several hours, nowhere near fast enough to tear itself apart. It wasn't close enough to the Sun for tidal disruption. The tidal forces at 12 million kilometers from the Sun are significant, but they're not strong enough to rip apart a comet nucleus several kilometers wide. That leaves thermal stress, and this is the explanation most astronomers are leaning toward. But here's the problem. The thermal models say it shouldn't have happened where it did. Dr. Matthew Knight from the U.S. Naval Academy, who has studied dozens of disintegrating comets, analyzed Atlas's light curve, the graph of how its brightness changed over time. What he found was striking. There was no evidence of a major outburst before the fragmentation. When comets break apart due to thermal stress, you typically see a sudden brightening as fresh ice is exposed and begins outgassing rapidly. That brightening can last for hours or even days. But with Atlas, the brightening was minimal. One day it was there, behaving normally. The next day it was gone. It was almost as if the comet just switched off. This has led to some really interesting speculation. What if Atlas didn't fragment in the traditional sense? What if something else happened? What if the nucleus, instead of breaking into large pieces, suddenly crumbled into a cloud of dust particles, too small to hold together or reflect much light? What if there was some kind of internal collapse, where the structure that was holding the loosely bound nucleus together just failed all at once? This is where we start to venture into truly speculative territory. But stay with me, because this is where it gets mind-blowing. What if comet nuclei aren't just piles of ice and rock held together by weak gravity and ice bonds? What if there's something else, some additional structural element we haven't properly accounted for? There's a concept in planetary science called sintering, and it might be the key to understanding Atlas. Sintering is a process where particles bond together without melting, usually through a combination of pressure and atomic diffusion over long periods of time. Think of it like this. If you leave a snowball sitting in your freezer for months, the snow crystals slowly bond together more tightly, and the snowball becomes harder and more solid, even though it never melted. In the outer solar system, where temperatures are incredibly low and timescales are incredibly long, sintering can create surprisingly strong structures from what should be loose, fluffy material. Scientists have theorized that the nuclei of Oort cloud comets might be partially sintered, with their particles bonded together more strongly than we'd expect just from ice and gravity alone. This would explain why many sun-grazers can get so close to the sun before disintegrating. They're not just held together by weak forces. They have real structural integrity built up over billions of years of sintering in the deep freeze of the Oort cloud. But here's the terrifying implication. If sintering is what gives comet nuclei their strength, then what happens when that sintered structure fails? What if, when the temperature gets high enough, the bonds created by billions of years of sintering all break at once? The comet wouldn't crack or split. It would just collapse into its constituent particles, transforming almost instantly from a solid object into a diffuse cloud of dust. And from Earth, it would look exactly like what we saw with Atlas. One day there, the next day gone. If this is what happened, then it suggests something deeply unsettling. We don't actually understand the structural properties of comet nuclei as well as we thought we did. And if we don't understand that, then all of our predictions about which comets will survive their approach to the sun and which won't are built on a foundation of sand. Now, you might still be thinking, okay, so we don't understand comets perfectly. So what? How does this affect me? Why should I care about one comet breaking apart? And that's a fair question. Let me answer it by asking you to imagine something. Imagine that tomorrow, astronomers discover a new comet. It's big, maybe 10 kilometers across, and it's on a trajectory that will bring it close to the sun. Really close. Sun grazing close. Based on our models, scientists calculate that it should survive the encounter and emerge on the other side. There's no threat to Earth. The comet's orbit doesn't come anywhere near our planet. Everything looks safe. But what if the scientists are wrong? What if, like Atlas, this comet disintegrates earlier than predicted? And what if, instead of being 12 million kilometers from the sun when it breaks apart, it's only a few million kilometers away? At that distance, the sun's gravity is incredibly strong. When the comet fragments, those pieces don't just drift apart. They get scattered. Some fall into the sun, but others? Others might get deflected onto new trajectories. Trajectories we didn't predict. Trajectories that might, just possibly, intersect with Earth's orbit. This isn't science fiction. This is a real concern among planetary defense experts. Dr. Paul Chodas, the director of NASA's Center for Near-Earth Object Studies, has pointed out that unpredictable comet fragmentation is one of the biggest challenges in assessing impact threats. When a comet breaks apart, we essentially have multiple new objects to track, each with its own orbit, and those orbits can be very different from the original comet's path. If we don't understand when and how comets fragment, we can't accurately predict the risk they pose. And here's the really scary part. Comets are fast. Really fast. They're coming in from the outer solar system, falling toward the sun under its gravitational pull, and by the time they cross Earth's orbit, they can be traveling at speeds of 50, 60, even 70 kilometers per second. That's over 150,000 miles per hour. At those speeds, even a relatively small fragment, just a few hundred meters across, carries devastating kinetic energy. If something like that hit Earth, the consequences would be catastrophic. The Tunguska event of 1908, which flattened 2,000 square kilometers of Siberian forest, was probably caused by a comet or asteroid fragment only about 50 meters across. The Chelyabinsk meteor of 2013, which injured over 1,500 people when it exploded over Russia, was only about 20 meters wide. Now imagine something a kilometer across, or 5 kilometers, or 10. We're talking about extinction-level events. We're talking about impacts that could end human civilization. And the thing is, we have very little warning time for comets. Unlike asteroids, which orbit mostly in the inner solar system, where we can track them years in advance, comets can come from the Oort cloud with very little notice. Atlas was discovered only about a month before it disintegrated. A month. If Atlas had been on a collision course with Earth and had fragmented in a way that sent debris our way, we would have had less than 4 weeks to prepare. That's not enough time to evacuate cities. It's not enough time to mount any kind of meaningful defense. It's barely enough time to say goodbye. This is why Atlas matters. Not because one comet broke apart, but because it revealed that our understanding of comet behavior has serious gaps. And those gaps represent genuine danger. We can't defend against threats we can't predict. We can't track fragments we didn't know would exist. And if comets like Atlas can defy our models and disintegrate in ways we don't expect, then we are more vulnerable than we realized. But let's zoom out even further, because there's another layer to this story that we need to explore. Atlas isn't just about one comet, or even about the threat of impacts. It's about what it reveals about the nature of our solar system and our place in it. You see, we live in what astronomers call a relatively stable period of solar system history. The planets are in settled orbits. The major planetesimals have already accreted or been ejected. The late heavy bombardment, a period about 4 billion years ago when the inner solar system was pummeled by impacts, is long over. we're in a comfortable, predictable cosmic environment. Or so we thought. But the Oort cloud is a reminder that we're not as safe as we like to believe. Out there, in the darkness beyond Pluto, there are trillions of cometary nuclei. Trillions. Each one a potential visitor, each one a possible threat. And here's what keeps planetary scientists up at night. We don't know what might disturb them. We don't know what might send thousands or millions of them streaming toward the inner solar system all at once. A passing star could do it. Stars move through the galaxy, and occasionally, one passes close enough to our solar system to gravitationally disturb the Oort cloud. The last time this happened was about 70,000 years ago, when a red dwarf called Schulz's star passed within about 1 light-year of the Sun. That's incredibly close in astronomical terms. The gravitational perturbation from that passage might have sent countless comets falling toward the inner solar system, though it would take hundreds of thousands of years for them to arrive. A close encounter with a molecular cloud could do it. As our solar system orbits the galaxy, it occasionally passes through regions of dense interstellar gas and dust. The gravitational effects of such a cloud could disturb the Oort cloud, triggering a comet shower. Even the gravitational influence of the Milky Way itself, the galactic tide, can perturb objects in the Oort cloud over long timescales. This might be responsible for a baseline rate of comet arrivals, a steady trickle of visitors from the deep freeze. But here's the truly unsettling thought. What if there's already a disturbance propagating through the Oort cloud right now? What if, thousands of years ago, something happened, some gravitational perturbation we don't know about, and right now, at this very moment, there's a swarm of comets headed our way? They're still too far out to detect, still years or decades away from entering the inner solar system. But they're coming, and we won't know about it until they start arriving. This sounds like science fiction, but it's a scenario that scientists take seriously. Dr. Nathan Cobb from the Planetary Science Institute has run computer simulations of Oort cloud dynamics, and he's found that disturbances can create waves of comets arriving over periods of 1 million years or more. If we're currently in one of these waves, we might see a higher than average rate of comet arrivals for millennia to come. And if we don't understand how these comets behave, if objects like Atlas keep surprising us, then we're facing those threats blind. Now, I want to shift gears slightly and talk about something that might seem unrelated, but is actually crucial for understanding the full significance of Atlas, the history of comet observation, and how it's changed our understanding of the universe. For most of human history, comets were seen as supernatural events. They were omens, signs from the gods, harbingers of disaster. This wasn't entirely irrational. Comets are bright, they're unexpected, they look like nothing else in the sky. And they're rare enough that when one appears, it feels like something significant. Cultures all over the world developed myths and legends about comets, almost always associating them with change, upheaval, or catastrophe. The shift from viewing comets as omens to understanding them as natural objects following predictable laws was one of the great intellectual revolutions of the scientific revolution. In 1577, the Danish astronomer Tycho Brahe made careful observations of a great comet and proved that it was beyond the moon, traveling through the space between planets. This was shocking at the time because the prevailing Aristotelian view held that the heavens were perfect and unchanging. Comets couldn't be celestial objects because that would mean the heavens weren't perfect. Tycho's observations shattered that worldview. Then, in 1705, Edmund Halley did something remarkable. He studied the historical records of comet sightings and noticed that comets had appeared at roughly 76-year intervals in 1531, 1607, and 1682. He realized these weren't different comets. They were the same comet, returning periodically as it orbited the sun. He predicted it would return in 1758. He died in 1742, but his prediction was vindicated when the comet reappeared on Christmas Day, 1758. It's been known as Halley's Comet ever since. This was a profound moment in the history of science. It proved that comets followed Newton's laws of motion and gravitation. They weren't omens or supernatural events. They were just rocks and ice following orbits, as predictable and natural as the planets themselves. The universe was revealed to be a clockwork mechanism, operating according to fixed laws that humans could discover and understand. Except, as Atlas is now reminding us, it's not that simple. The universe isn't a clockwork. It's messier, more chaotic, more surprising than that elegant Newtonian picture suggested. Comets do follow predictable orbits, but their physical evolution as they approach the sun is anything but predictable. And the more we study them, the more exceptions and anomalies we find. This is part of a broader pattern in the history of science. We create models to explain observations. The models work pretty well most of the time. We get confident, maybe overconfident, in our understanding. And then something like Atlas comes along and reminds us that we don't know as much as we thought we did. The universe is under no obligation to fit our models. Reality is always more complex, more subtle, more full of surprises than our theories can capture. And here's where this connects to the black swan concept again. Black swan events happen when we mistake the limits of our knowledge for the limits of what's possible. We think, we've never seen this happen before, so it probably won't happen. But the universe is vast and old, and just because we haven't observed something in our tiny window of observation doesn't mean it's impossible, or even rare on cosmic timescales. Think about it this way. Modern astronomy is only a few centuries old. We've been seriously observing comets with telescopes for maybe 400 years. That sounds like a long time from a human perspective, but in astronomical terms, it's nothing. It's a blink. It's like watching the ocean for 10 seconds and concluding you understand everything about waves because you didn't happen to see a tsunami during your observation period. The absence of evidence is not evidence of absence, and our limited observation window might have given us a dangerously incomplete picture of what comets can actually do. Dr. Carrie Leese from Johns Hopkins Applied Physics Laboratory has pointed out something fascinating. When we look at the asteroid belt between Mars and Jupiter, we find countless small bodies, rocky remnants from the solar system's formation. But we also find something unexpected. We find rocks that show evidence of catastrophic collisions, objects that were once part of larger bodies that were completely shattered by impacts. The asteroid belt isn't just a collection of pristine building blocks. It's a graveyard full of the remains of objects that met violent ends. Now, what if the same is true for comets? What if the Oort cloud isn't just a peaceful storage facility of pristine icy objects? What if it's also a graveyard, full of damaged, fragmented, structurally compromised objects that have been involved in collisions or near misses over billions of years? When one of these damaged objects falls toward the sun, it might look normal at first, but it might be hiding catastrophic structural weaknesses that only become apparent under stress. And if that's the case, then our models, which assume comets are relatively uniform and pristine, are fundamentally flawed. This brings us to a really uncomfortable question. How many other Atlas-like events have we missed? How many comets have disintegrated in ways that surprised us, that didn't match our predictions, but we wrote them off as anomalies and moved on? When you start looking at the historical record with this question in mind, a disturbing pattern emerges. In 1996, Comet Hyakutake passed close to Earth and became one of the brightest comets in decades. But as it approached the sun, it began fragmenting in ways that puzzled astronomers. It survived its perihelion passage, but just barely, and it showed signs of internal structure that didn't match the simple, dirty snowball model. In 1999, Comet LINEAR C 1999 S4 broke apart into dozens of pieces as it approached the sun. The fragmentation began earlier than expected and proceeded more rapidly than models predicted. By the time it reached perihelion, the comet had essentially vanished, leaving only a diffuse cloud of debris. In 2006, Comet 73 P. Schwarzmann-Wachmann 3 split into at least 68 distinct fragments during its approach to the Sun. Some fragments survived, others disintegrated, and the pattern of breakup didn't match any single model. It seemed like each fragment had its own unique structural properties. And these are just the well-documented cases, the bright comets that were being closely monitored. How many fainter comets disintegrated in surprising ways when no one was watching closely? How many potential Atlas events did we miss because we weren't paying attention, or because we didn't have the observational tools to catch them? The Atlas survey that discovered our current comet is only about a decade old. SOHO has been observing sun grazers for less than 30 years. Most of our really detailed comet observations are from the past few decades at most. We're still in the early stages of systematically studying these objects, and what we're learning is that every comet is unique, every approach to the Sun is different, and the exceptions are far more common than the rules. This should humble us. It should make us question our confidence in predicting comet behavior. And it should make us wonder, what else don't we know? Let me take you deeper into the physics of what happens when a comet approaches the Sun, because this is where the story gets truly mind-bending, and it's crucial for understanding why Atlas is such a puzzle. When a comet is out in the Oort cloud, it's at a temperature of about 3 to 4 Kelvin. That's just a few degrees above absolute zero, the coldest temperature possible in the universe. At that temperature, everything is frozen solid. Not just water ice, but also carbon dioxide, methane, ammonia, nitrogen, carbon monoxide, all the volatile compounds that are common in the outer solar system. The comet is a time capsule, perfectly preserved with the same composition it's had since the solar system formed. As the comet falls toward the Sun, it begins to warm up. But it doesn't warm evenly. The side facing the Sun heats up first, while the interior and the shadowed side remain frozen. This creates extreme temperature gradients within the nucleus. The surface might be at 200 Kelvin, while a meter below the surface, it's still at 50 Kelvin. These gradients create stress, pressure, and complex thermodynamic processes that we're only beginning to understand. Here's where it gets really interesting. When ice sublimates, turning directly from solid to gas, without going through a liquid phase, it doesn't just evaporate gently. At the temperatures and pressures inside a comet nucleus, sublimation can be explosive. Imagine pockets of frozen gas trapped beneath a layer of ice and dust. As the Sun heats the surface, these pockets warm up and the pressure inside them increases. If the overlying material is strong enough, the pressure can build to tremendous levels before finally breaking through in a violent outburst. Dr. Michael Belton from Belton Space Exploration Initiatives has studied these outbursts extensively, and he's found that they can be incredibly powerful. A single outburst can eject thousands of tons of material into space in a matter of minutes. And because the gas is escaping from a localized area, it creates a jet, a focused stream of vapor and dust that acts like a rocket engine, pushing the comet and potentially altering its rotation. Now, imagine hundreds of thousands of these outbursts happening all over the nucleus as the comet gets closer to the Sun. Each one is changing the Sun, comet's rotation slightly, creating new cracks and weak points, excavating cavities beneath the surface. The nucleus becomes riddled with voids and fractures. It's not a solid object anymore. It's more like a foam, a lattice of ice and rock with huge empty spaces between the solid material. And it's all being held together by material strength that's being constantly degraded by thermal stress and outgassing. At some point, there's a tipping point. The structure becomes so weakened, so riddled with cracks and voids, that it can no longer support itself. And when that happens, the collapse can be catastrophic and rapid. This might be what happened to Atlas. After weeks of heating and outgassing, after countless small outbursts creating countless small fractures, the internal structure finally failed. And when it failed, The entire nucleus, several kilometers of ice and rock, just collapsed into a cloud of debris. But here's what makes Atlas special, what makes it potentially a black swan event. The collapse happened earlier than it should have. The models say that for a comet of Atlas's size, at the distance it was from the sun when it disintegrated, the thermal stress shouldn't have been enough to cause total structural failure. Something else must have been going on. Either the comet was weaker than we thought, or the stresses on it were greater than we calculated, or there's some physical process we don't understand that contributed to the breakup. And this is where we need to talk about some really speculative but fascinating ideas. What if comet nuclei contain trapped gases under pressure, gases that have been locked inside since the comet's formation billions of years ago? As the sun heats the nucleus, these gases warm up and expand. The pressure increases. If the nucleus contains large reservoirs of trapped gas, the internal pressure could reach levels high enough to blow the entire structure apart from the inside, like a bomb. There's some evidence for this. When NASA's Deep Impact Probe crashed into Comet Tempel 1, the impact excavated a crater and ejected a plume of material. But the composition of that plume was puzzling. It contained far more volatile material than expected, suggesting that there were reservoirs of gas trapped beneath the surface. And the crater was much bigger than predicted, suggesting the interior was less dense, more porous than expected. What if Atlas had large internal voids filled with pressurized gas? As the comet heated up, those voids would have heated up too, and the pressure inside them would have increased dramatically. Some point, the pressure might have exceeded the structural strength of the surrounding material, causing a catastrophic failure. The comet didn't break apart because of surface heating. It exploded from the inside. This is speculative. I want to be clear about that. We don't have direct evidence that this is what happened to Atlas, but it's a hypothesis that fits the observations and would explain why the disintegration happened earlier than predicted. And if this hypothesis is correct, it has profound implications for how we assess the risk from comets, because it means that even large, seemingly stable comets could be ticking time bombs, waiting for the right conditions to trigger an internal explosion. Now let's talk about something that might seem like a tangent, but is actually deeply connected to everything we've been discussing: the role of probability and prediction in science. Science, at its core, is about making predictions. We observe patterns, we construct theories to explain those patterns, and then we use those theories to predict what will happen in new situations. When our predictions are accurate, we gain confidence in our theories. When our predictions fail, we know our theories need revision. This is the scientific method, and it's given us tremendous power to understand and manipulate the natural world. But there's a problem. Some systems are inherently unpredictable, not because we don't know enough about them, but because they're fundamentally chaotic. A chaotic system is one where tiny differences in initial conditions lead to wildly different outcomes. The classic example is weather. We can predict the weather pretty accurately for a few days, reasonably well for a week, but beyond about 2 weeks, our predictions become essentially useless. This isn't because we don't understand atmospheric physics. It's because the atmosphere is a chaotic system, and chaos makes long-term prediction impossible. Comet behavior might be chaotic in the same way. Even if we perfectly understood all the physics involved, even if we knew the exact composition and structure of a comet nucleus, we still might not be able to predict whether it will disintegrate or survive, because that outcome might depend on tiny details that we can't measure and that amplify over time through chaotic dynamics. Dr. Brett Gladman from the University of British Columbia has studied the long-term dynamics of small bodies in the solar system, and he's found that their orbits are often chaotic on timescales of thousands to millions of years. Small gravitational perturbations from the planets can accumulate and amplify, leading to outcomes that are essentially unpredictable. An asteroid might orbit stably for 1 million years, and then, due to a tiny perturbation at just the right time, It kicked into a planet-crossing orbit. There's no way to predict this far in advance, because the system is chaotic. If comet disintegration is similarly chaotic, then Atlas isn't just an anomaly we can explain away. It's a demonstration that we're trying to predict an inherently unpredictable phenomenon. And that's a very different problem. It means no matter how much we study comets, no matter how much data we collect, we'll never be able to say with certainty whether a particular comet will survive its approach to the sun. We can give probabilities, but there will always be surprises. There will always be black swans. This has profound implications for planetary defense. If we can't reliably predict when comets will fragment, we can't reliably assess the threat they pose. A comet that looks safe might disintegrate and send debris toward Earth. A comet that looks dangerous might hold together and pass harmlessly by. We're playing a game of probability where the odds are fundamentally uncertain. But here's the thing. We can't just throw up our hands and say, it's all unpredictable, so why bother? We have to try. We have to study every comet we can, collect as much data as possible, refine our models, and hope that even if we can't achieve perfect prediction, we can at least improve our odds. And sometimes, events like Atlas, surprising as they are, actually help us by revealing the gaps in our understanding. Let me share something with you that really drives home why this matters on a personal level. In 2013, the Chelyabinsk meteor exploded over Russia. It was a small asteroid, only about 20 meters across, and nobody saw it coming. It approached from the direction of the sun, so it was invisible to our ground-based telescopes. When it hit the atmosphere, traveling at about 19 kilometers per second, it exploded with the force of about 500 kilotons of TNT. That's about 30 times the energy of the Hiroshima atomic bomb. The shockwave shattered windows across the city of Chelyabinsk. Over 1,500 people were injured, most of them from flying glass. People were going about their morning routines, and suddenly, without warning, the sky lit up brighter than the sun, and a few minutes later, a shockwave shattered windows and collapsed roofs. It was terrifying and completely unexpected. Now, imagine if that object had been 5 times larger, or 10 times larger. Instead of injuring 1,500 people, it might have killed tens of thousands or hundreds of thousands. And we would have had no warning. None. It would have just appeared out of the sky and ended countless lives in an instant. This is the reality we live in. We're in a cosmic shooting gallery, and we don't see most of the bullets. And comets are some of the fastest, most dangerous bullets in that gallery. If a comet fragments in just the wrong way, at just the wrong time, it could send a city killer, or even a civilization ender toward us with very little warning. And if our models can't predict when and how comets will fragment, then we're even more vulnerable than we thought. I want to be clear. I'm not trying to scare you unnecessarily. The odds of a major impact in any given year are extremely low. But over long enough timescales, impacts are inevitable. We know this because we can see the craters on Earth, on the Moon, on every solid body in the solar system. Impacts happen. And the question isn't whether another major impact will occur, but when and whether we'll be ready for it. Atlas is important because it's a reminder that we're not ready. Not yet. We're making progress. We're getting better at tracking near-Earth objects. We're developing deflection technologies. NASA's DART mission in 2022 proved that we can alter the orbit of an asteroid by ramming a spacecraft into it. But all of this depends on detection and prediction. If we can't see the threat coming, if we can't predict how it will behave, then all our deflection technology is useless. And this brings us to the deeper philosophical question that I think Atlas really forces us to confront. How do we live with uncertainty? How do we make decisions and plans when we know that we don't fully understand the universe we live in? When we know that black swan events can upend everything without warning? This isn't just a question about comets. It's a question about life. We all make plans assuming that the future will be reasonably similar to the past. We assume the sun will rise tomorrow, that the ground beneath our feet will remain solid, that the laws of nature will continue operating as they always have. And most of the time, these assumptions are correct. The universe is, for the most part, regular and predictable. But not always. Sometimes, without warning, everything changes. A pandemic sweeps across the world. A financial system collapses. A comet does something comets aren't supposed to do. These black swan events remind us that our sense of security, our feeling that we understand and can control our environment, is partly an illusion. The universe is fundamentally uncertain, and all our knowledge and technology can't eliminate that uncertainty. They can only help us manage it. So what do we do with this knowledge? Do we become paralyzed by fear, constantly worrying about all the things that could go wrong? That would be a terrible way to live, and it wouldn't actually make us any safer. Or do we ignore the uncertainty, pretend that everything is fine, that the risks aren't real? That's equally problematic, because it leaves us unprepared when something does go wrong. The answer, I think, is to embrace what Nassim Taleb calls anti-fragility. Instead of trying to predict and prevent every possible disaster, which is impossible, we should focus on building systems and societies that can survive and even benefit from unexpected shocks. We should invest in resilience, redundancy, and adaptability. We should maintain healthy skepticism about our models and predictions, always remembering that reality is more complex than our theories. And we should stay curious, keep learning, keep pushing the boundaries of our understanding, because every new piece of knowledge, even knowledge of our own ignorance, makes us a little bit safer. Atlas is a gift in this sense. It's uncomfortable, sure. It challenges our confidence and reveals our blind spots. But it's also an opportunity to learn, to improve our models, to recognize what we don't know. And that recognition is the first step toward addressing the gaps in our understanding. Now, I want to shift focus slightly and talk about the broader context of what's happening in astronomy right now, because Atlas is part of a larger pattern of discoveries that are forcing us to rethink our understanding of the solar system. In the past couple of decades, we've discovered that the solar system is far more dynamic and complex than we previously believed. We found that the giant planets probably migrated significantly from their original positions early in solar system history, a period called the Late Heavy Bombardment, when Jupiter, Saturn, Uranus, and Neptune moved around, gravitationally scattering smaller bodies and triggering a massive bombardment of the inner solar system. This explains some otherwise puzzling features of the planet's orbits and the distribution of asteroids and comets. We've discovered thousands of objects in the Kuiper Belt, and they're not distributed the way we expected. Some of them have very strange orbits that can't be easily explained by the influence of the known planets. This has led to speculation about a possible ninth planet, a large object lurking in the outer solar system that we haven't detected yet, but whose gravitational influence might explain these anomalies. We found that comets are more diverse than we thought. Some are rich in water ice, others in carbon dioxide. Some are fluffy and fragile, others are surprisingly solid. Some outgas symmetrically, others produce enormous jets from isolated active regions. There isn't a simple, typical comet. Every one is unique. And we've discovered that the boundary between comets and asteroids is blurrier than we thought. Some objects that orbit like asteroids occasionally develop comet-like tails, suggesting they have ice beneath their surfaces. Some objects that should be icy comets show no activity at all. The old classification system, where comets were icy and from the outer system, while asteroids were rocky and from the inner system, is breaking down. We're realizing that these are artificial categories, and reality is Messier. What all of this suggests is that we're still in the early stages of understanding our cosmic neighborhood. Despite centuries of observation and decades of space exploration, we're still being surprised on a regular basis. And Atlas is just the latest in a long series of surprises. But here's what's exciting about this. Every surprise is an opportunity to learn something new. Every time our predictions fail, we get a chance to build better models. Science doesn't progress smoothly and steadily. It progresses in fits and starts, with long periods of gradual refinement punctuated by sudden revelations that overturn our understanding. Atlas might be one of those revelations. It might be the observation that forces us to fundamentally rethink how we model comet structure and behavior. And if that happens, if Atlas leads to a major advance in our understanding, then future historians of science will look back on this moment as pivotal. They'll say, that was when astronomers realized they needed to account for internal structure and trapped volatiles in their models. That was when the field of comet science matured from simple physics to complex systems analysis. We might be living through one of those transformative moments right now, and we don't even fully realize it yet. Let's talk about what happens next, both for the scientific study of Atlas specifically and for comet science more broadly. Right now, astronomers around the world are analyzing every piece of data they collected on Atlas. They're poring over images taken before the disintegration, looking for any subtle signs they might have missed. They're studying the spectrum of light from the comet, which can reveal its composition. They're measuring the size and distribution of the dust cloud that's all that remains of the nucleus. Every piece of information is a clue. They're also comparing Atlas to other disintegrated comets, looking for patterns. Are there commonalities between Atlas and Comet Isan, or Comet LINEAR, or the dozens of other sun-grazers that have broken apart over the years? Are there signatures, observable warning signs that a comet is about to disintegrate? If so, identifying those signatures could dramatically improve our predictive ability. Theoretical physicists are revisiting their models of comet structure and fragmentation. They're running computer simulations with different assumptions about internal structure, trapped gases, material strength, thermal conductivity. They're trying to recreate what happened to Atlas in silico, and if they can match the observations, that will tell them what conditions must have existed inside the nucleus. And space agencies are planning future missions. Understanding comets isn't just an academic exercise. It has practical implications for planetary defense, for resource utilization in space, and for understanding the origin of Earth's water and organic molecules. Future missions might target comets similar to Atlas, trying to study them up close before they disintegrate. We might send probes equipped with ground-penetrating radar to map the internal structure of a comet nucleus. We might even attempt to land on a comet that's approaching the sun and ride it as it becomes active, collecting data from the inside. The European Space Agency's Rosetta mission, which orbited Comet 67P, Churyumov-Gerasimenko, from 2014 to 2016, and even landed a probe on its surface, gave us unprecedented insights into comet composition and activity. But it studied a relatively stable, well-behaved comet. Imagine a mission to a comet like Atlas, one that's on a sun-grazing trajectory, one that's likely to disintegrate. The data from such a mission would be invaluable. Dangerous, risky, technically challenging, but invaluable. We're also developing better ground-based observation capabilities. The Vera C. Rubin Observatory, currently under construction in Chile, will scan the entire visible sky every few nights when it becomes operational. It will discover thousands of new comets and asteroids, and it will track known objects with unprecedented precision. The data from this observatory will revolutionize our understanding of small body populations and dynamics. So the study of comets is entering a new era, an era of big data, sophisticated modeling, and ambitious space missions. Atlas is a reminder of why this work is important and why we need to keep pushing forward. But beyond the science, I want to talk about what Atlas means for how we see ourselves and our place in the universe. Because I think this is where the real significance lies, beyond the technical details and the threat assessments. Humans have always looked to the sky for meaning. The stars and planets were gods or the homes of gods. Eclipses and comets were omens. The heavens were a mirror in which we saw our own dramas and destinies reflected. And in some ways, we still do this. We're pattern-seeking creatures. We can't help but find meaning in the cosmos. But the scientific revolution taught us that the universe doesn't actually care about us. The planets aren't gods. Comets aren't omens. The universe is just matter and energy following physical laws, indifferent to human hopes and fears. This was a profound realization, both liberating and terrifying. Liberating because it meant we weren't at the mercy of capricious divine forces. Terrifying because it meant we were alone, insignificant specks in an uncaring cosmos. And yet, here we are, discussing a comet, talking about its significance, debating what it means. In a way, we've come full circle. Comets are meaningful again, not because they're omens sent by gods, but because they're part of a universe we're trying to understand, and our survival might depend on that understanding. Atlas matters because it challenges us. It says, "You think you understand comets? Think again." It humbles us. And that humility is important. It keeps us questioning, keeps us learning, keeps us from becoming complacent. But Atlas also empowers us, because we're not passive observers anymore. We're not ancient humans watching a light in the sky and wondering what it means. We're a technological species with spacecraft and telescopes and computers. We can study comets up close. We can track them. And increasingly, we can even defend ourselves against them. We're not at the mercy of cosmic forces. We're learning to navigate and manage them. This is an extraordinary moment in human history. We're the first generation with the capability to detect and potentially deflect extinction-level impacts. We're the first generation to send probes to comets and land on their surfaces. We're the first generation to have a comprehensive scientific understanding of what comets are and where they come from. Our ancestors could only wonder and fear. We can study and prepare. But with that capability comes responsibility. We need to take the threat seriously. We need to fund the surveys and tracking programs. We need to develop and test deflection technologies. We need to study events like Atlas and learn from them. Because the universe won't give us any special consideration. If a comet is on a collision course with Earth, it won't swerve to avoid us. Our only protection is our knowledge and our technology. And this brings me to something I find deeply moving. The fact that you're watching this video right now is a testament to humanity's progress. A few centuries ago, if a comet appeared in the sky, people could only look up at it and wonder. Today, you're able to access a detailed, scientifically accurate explanation of what comets are, how they behave, and why one particular comet's unexpected disintegration matters. You're participating in humanity's collective effort to understand the universe. That's remarkable. Every time you learn something about science, every time you engage with difficult concepts and expand your understanding, you're contributing to something larger than yourself. You're part of a civilization-wide project that spans generations, the project of understanding reality. And that project is how we survive and thrive in a universe that can be hostile. So when I ask you to subscribe to this channel, I'm not just asking for algorithmic support, though that matters too. I'm asking you to signal that this kind of content, deep, thoughtful, scientific exploration of challenging topics, is valuable. Because there are a lot of forces in our information ecosystem pushing toward superficiality, toward quick takes and hot opinions and content that doesn't require much thought. We need to push back against that. We need to create space for nuance, complexity, and genuine learning. Atlas is a complex story. There's no simple takeaway, no neat conclusion. It's a puzzle we're still trying to solve, and it raises more questions than it answers. But that's what makes it worth discussing. The easy questions have already been answered. The hard questions, the ones that force us to confront our ignorance and expand our understanding, Those are the ones that drive progress. Now, I want to address something that some of you might be thinking. This is all very interesting, but is it really a black swan event? Or are you overhyping it? That's a fair question, and I want to be honest about it. The truth is, we don't know yet. Atlas might turn out to be a significant anomaly that forces a major revision in our understanding of comets. Or it might turn out to be an outlier that doesn't fundamentally challenge our models. The jury is still out. What makes something a black swan event isn't just that it's unexpected. It's that it has major consequences and reveals fundamental flaws in our understanding. The 2008 financial crisis was a black swan because it revealed that the global financial system was far more fragile than economists and policymakers realized. It led to major reforms and a rethinking of financial regulation. For Atlas to be a true black swan in astronomy, it would need to lead to similar consequences. It would need to force a major revision in how we model comet behavior, with implications for planetary defense and our understanding of solar system dynamics. And it would need to make us realize that we were systematically underestimating the risk from comets. Is that what's happening? Maybe. The fact that Atlas disintegrated earlier and more completely than models predicted suggests there's something important we don't understand about comet structure or sublimation dynamics. If future comets behave similarly, if Atlas turns out to be an example of a common phenomenon we weren't accounting for, then yes, this could be a black swan moment. But it's also possible that Atlas was just weird, a statistical outlier with unique properties that don't generalize to other comets. Maybe it had an unusual composition, or an unusual structure, or just got unlucky with how thermal stresses happened to concentrate. If that's the case, then Atlas is interesting, but not transformative. Time will tell. Science doesn't work on the timescale of YouTube videos. It takes years or decades for the full significance of an observation to become clear. But I think it's worth paying attention to Atlas and to comet science more broadly, because there are hints that something interesting is happening, that we're on the verge of a deeper understanding. And even if Atlas doesn't turn out to be a black swan, the exercise of thinking about it in those terms is valuable. It forces us to question our assumptions, to examine our models critically, to consider what we might be missing. That kind of thinking is how science advances. Let me share one more perspective on this from the philosophy of science. There's a concept called the pessimistic meta-induction, which goes something like this. Throughout history, scientists have developed theories that they believed were true, that seemed to explain all the observations that appeared to be correct descriptions of reality. And then, eventually, those theories were shown to be wrong or incomplete. Newtonian mechanics gave way to relativity. Classical physics gave way to quantum mechanics. Every generation of scientists believes they finally figured it out, and every generation is eventually proven wrong. This pattern suggests we should be skeptical of our current theories. Our best models today, the ones that seem to explain everything, will probably also turn out to be wrong or incomplete eventually. We can't know for sure what their flaws are, but we can be confident they have flaws. This might seem depressing, like all our efforts are futile, but I think it's actually liberating. It means there's always more to discover. No matter how much we've learned, we're never done. There's always another layer of reality waiting to be revealed. And events like Atlas, moments when our predictions fail, are glimpses of that deeper reality. They're invitations to go further, to dig deeper, to expand our understanding. So yes, our current models of comet behavior might be wrong. They probably are wrong in some way. But that's not a failure. That's how science works. We create models. We test them against reality, and when they fail, we build better ones. Each iteration gets us closer to truth, even if we never reach it completely. And here's the beautiful thing. You're part of this process. By watching this video, by thinking about these questions, by staying curious and engaged, you're contributing to the collective human effort to understand the universe. You might not be a professional astronomer, but you're part of the community of people who care about these questions, and that matters. Let's bring this back to something more concrete and immediate. What can you, personally, do with the information you've learned today? First, you can look up. Seriously, go outside on a clear night and look at the stars. Download a stargazing app on your phone that will help you identify what you're seeing. The next time there's a visible comet, make the effort to see it. There's something profound about witnessing these cosmic visitors with your own eyes, about connecting with the same sight that has awed humans for millennia. It changes your perspective. It makes the universe feel more real and present. Second, you can stay informed. Follow astronomy news. NASA, ESA, and other space agencies regularly publish updates about new discoveries and ongoing missions. Science news outlets cover major astronomical events. By staying engaged, you'll be among the first to know if something significant happens, if a potentially dangerous object is discovered, if a new mission launches, if a major breakthrough occurs. Third, you can support space science. This doesn't necessarily mean donating money, though organizations like the Planetary Society do important work and appreciate support. It means advocating for science funding, voting for policymakers who take space science seriously, and pushing back against misinformation. When you see someone spreading flat Earth nonsense or claiming that space exploration is a waste of money, don't just scroll past. Engage respectfully but firmly. Explain why this work matters. Fourth, and this might be the most important, you can embrace the mindset of scientific thinking in your daily life. Question your assumptions. Look for evidence. Be willing to change your mind when new information comes to light. Acknowledge uncertainty instead of pretending you know more than you do. These habits of thought, cultivated by engaging with science, make you a better thinker and decision maker in all areas of life. The world is full of people who are certain about everything, who never question their beliefs, who interpret every new piece of information as confirmation of what they already thought. These people are intellectually fragile. When reality inevitably contradicts their beliefs, they can't adapt. They double down, they reject the evidence, they retreat into conspiracy theories. Don't be that person. Be antifragile. Be someone who gets stronger from being wrong, who treats surprises as opportunities to learn. Events like Atlas are training exercises for this mindset. They show us that the universe is more complex than we thought, and instead of being threatened by that, we should be excited. Now, let's talk about the future, because this is where things get really interesting. What's going to happen in the next few years, the next few decades, in terms of comet science and planetary defense? In the short term, we're going to see more observations like Atlas, the Atlas Survey, the Catalina Sky Survey, Pan-STARRS, and soon the Vera Rubin Observatory are constantly scanning the sky, finding new objects. On average, we discover several new comets every month. Most of them are faint and distant, not particularly interesting. But every so often, we find something special. A bright comet that will put on a good show. A close approaching comet that will pass near Earth. Or a strange comet like Atlas that challenges our understanding. Each of these discoveries is an opportunity to learn. And with modern technology, we can study these objects in far more detail than was possible even a decade ago. We have better telescopes, better instruments, better analysis techniques. Every comet that comes through the inner solar system now gets scrutinized by dozens of professional and amateur astronomers around the world, all collecting data, all contributing to our collective understanding. In the medium term, we're going to see new space missions to comets. NASA is currently considering several proposals for comet missions, including one that would visit multiple comets in a single mission, collecting samples from each. The European Space Agency and JAXA, the Japanese Space Agency, are also planning comet missions. Within the next 10 to 20 years, we might have spacecraft visiting several new comets. potentially including some that are on sun-grazing trajectories similar to Atlas. These missions won't just observe from a distance. We're talking about close flybys, orbiting, landing, and possibly even sample return. Imagine getting pieces of a comet back to Earth laboratories where we can analyze them with instruments far more sophisticated than anything we can put on a spacecraft. That would be revolutionary. We could determine the exact composition, measure the material strength, analyze the internal structure at microscopic scales. Every question we have about comet properties could be answered definitively. And here's something that sounds like science fiction, but is actually being seriously discussed: comet deflection tests. Just as NASA's DART mission tested asteroid deflection by ramming a spacecraft into an asteroid, we might attempt similar tests with comets. This would serve two purposes. First, it would demonstrate our capability to alter a comet's trajectory if we needed to. Second, and this is crucial, it would tell us about the internal structure and mechanical properties of comets. When you hit a solid rock with a spacecraft, it responds one way. When you hit a loosely bound pile of rubble, it responds differently. The response tells you what you're dealing with. Now, a comet deflection test would be more challenging than an asteroid deflection test because comets are more fragile and unpredictable. But that's exactly why we need to do it. We need to know whether our deflection techniques that work on asteroids will also work on comets, or whether comets require different approaches. In the longer term, and this is where we move into more speculative territory, we might develop early warning systems specifically for comets. Right now, our surveys are designed to find objects that come close to Earth. But what if we place telescopes in the outer solar system, maybe on Jupiter or Saturn's moons, specifically to watch for incoming comets? We could potentially detect long-period comets years, or even decades before they enter the inner solar system, giving us much more time to prepare if one turns out to be dangerous. We might also develop sophisticated models that can predict comet behavior with much greater accuracy. This would require collecting data on hundreds or thousands of comets, building a comprehensive database of their properties and behaviors. Machine learning algorithms could then analyze this data, identifying patterns and correlations that human scientists might miss. Eventually, we might be able to say with reasonable confidence, this comet has these properties, it's on this trajectory, and based on similar comets we've observed, there's an X% chance it will disintegrate at this distance from the Sun. But here's something even more ambitious that some scientists are discussing: active management of the comet threat. Instead of just tracking comets and hoping none of them pose a danger, what if we could actively reduce the number of dangerous comets in the solar system? One proposal involves using gravitational tractors or kinetic impactors to slightly alter the orbits of newly discovered Oort cloud comets while they're still far from the Sun. A tiny change in trajectory when a comet is at aphelion, its farthest point from the Sun, can result in a large change in where it goes when it reaches the inner solar system. We could potentially steer comets away from Earth-crossing orbits, ensuring they never pose a threat. Another, more radical proposal involves actually mining comets for resources. Comets contain water, organic compounds, and other materials that could be valuable for space exploration, and even for sustaining human presence in space. If we develop the technology to intercept and process cometary material, we'd gain intimate knowledge of comet structure and composition. We'd also be reducing the mass of potentially dangerous objects. A comet that's been mined and broken into small pieces is far less threatening than an intact, kilometer-sized nucleus. These ideas are speculative, decades away from implementation. But they're being discussed seriously by people in the planetary science and space exploration communities. They represent a future where we're not just passive inhabitants of the solar system, hoping we don't get hit by something, but active managers of our cosmic environment. And this connects to an even larger vision: humanity as a spacefaring civilization. Right now, we're confined to Earth, with all our eggs in one basket. A single asteroid or comet impact could potentially end human civilization. But if we establish permanent settlements on the Moon, Mars, and eventually other worlds, we become resilient. We become a species that can survive cosmic catastrophes. Comets are part of this story. Understanding them, learning to predict and manage them, is one of the challenges we need to overcome to become a truly spacefaring species. Atlas, in its own small way, is contributing to this grand project by revealing gaps in our understanding that we need to address. Now, I want to step back and talk about something that might seem philosophical, but is actually deeply practical: the relationship between knowledge and safety. Throughout most of human history, we were at the mercy of natural forces we didn't understand. Diseases, earthquakes, storms, droughts, all struck without warning, and we had no defense except luck. Countless people died from causes that we now consider preventable. But as we developed scientific understanding, we gained the ability to protect ourselves. We learned what causes diseases and developed vaccines and antibiotics. We learned what causes earthquakes and built structures that can withstand them. We learned to predict storms and evacuate people before they hit. Knowledge, in other words, is literally life-saving. Every advance in scientific understanding has the potential to prevent suffering and death. And this is as true for astronomy as it is for medicine or engineering. Right now, the main thing protecting Earth from asteroid and comet impacts is luck. We happen to live in a period when the inner solar system is relatively clear of large impactors. But that could change. Impacts are inevitable over long enough timescales. Our only real defense is knowledge, knowing what objects exist, where they are, where they're going, and how to deflect them if necessary. Atlas is a reminder that our knowledge is incomplete. And incomplete knowledge is dangerous because it gives us false confidence. If we think we understand comet behavior, but we actually don't, we might underestimate threats or make wrong decisions about how to respond to them. But the solution isn't to despair about how much we don't know. The solution is to keep learning, keep questioning, keep pushing the boundaries of our understanding. Every comet we study, every anomaly we investigate, every model we refine, makes us a little bit safer. And here's something profound. You're part of that process. By caring about this topic, by engaging with the science, by supporting continued research and exploration, you're contributing to humanity's collective safety. That might sound grandiose, but it's true. Science isn't something that happens in isolation, done by lone geniuses in ivory towers. It's a collective enterprise, supported by societies that value knowledge and curiosity. When you signal that you care about these questions, you're helping to maintain that culture of curiosity. Let me share a story that illustrates why this matters. In 1908, a cosmic object exploded over Tunguska, Siberia, flattening 2,000 square kilometers of forest. If that explosion had happened over a populated area, it would have killed potentially hundreds of thousands of people. But because it happened in a remote region, casualties were minimal. We got lucky. For decades after the Tangshu-Ka event, nobody knew what had caused it. There were wild theories: a tiny black hole, antimatter, and alien spacecraft. It wasn't until much later, after we developed a better understanding of meteor physics and the nature of comets and asteroids, that we realized what had happened. A cosmic object, probably about 50 meters across, entered the atmosphere and exploded several kilometers above the ground. The airburst created a shockwave that flattened the forest. This realization was important because it told us that we don't need a direct ground impact to have a catastrophe. An airburst over a city would be devastating. And objects 50 meters across are relatively common in near-Earth space. There are probably hundreds of thousands of them. We've only cataloged a small fraction. So after understanding Tunguska, the scientific community began pushing for better survey programs to find and track these smaller objects. It's still an ongoing effort, but we've made progress. We're finding thousands of new near-Earth objects every year. And while we're still far from having a complete census, we're moving in the right direction. This is how knowledge leads to action, leads to greater safety. We observed something, Tunguska. We worked to understand it. That understanding revealed a threat we hadn't fully appreciated, and that led to efforts to address the threat. If we hadn't studied Tunguska, if we'd just written it off as a weird one-off event, we wouldn't have developed the survey programs we have today. We'd be more vulnerable. Atlas is potentially the same kind of wake-up call. It's showing us that comet behavior is more complex and less predictable than we thought. If we take that lesson seriously, it will lead to better models, more capable observation programs, and ultimately, better planetary defense. But only if we pay attention, only if we don't just dismiss it as an anomaly and move on. Now, let's talk about something that I find absolutely fascinating: the interconnectedness of cosmic events and how they ripple through the solar system in ways we're only beginning to understand. When you think about a comet disintegrating, you probably think of it as an isolated event. A comet breaks apart, turns into a cloud of dust, and that's the end of the story. But actually, comet fragmentation can have consequences that echo through the solar system for thousands or even millions of years. When a comet fragments, it creates a debris stream, a trail of particles spread out along the comet's original orbit. These particles continue orbiting the Sun, and if Earth's orbit happens to intersect with this debris stream, we get a meteor shower. Every time you see shooting stars during the Perseids in August or the Leonids in November, you're seeing Earth plowing through debris from ancient comet fragmentations. Most meteor showers are harmless, beautiful displays that pose no danger. The particles are tiny, typically the size of grains of sand, and they burn up harmlessly in the upper atmosphere. But here's the thing: not all the debris is small. Some fragments can be much larger. And if a larger fragment hits Earth, it doesn't burn up. It makes it to the ground as a meteorite. Or worse, it explodes in the atmosphere as a meteor airburst, like what happened at Tunguska. So comet fragmentations, even those that happen far from Earth, can create potential hazards that persist for millennia. Every time a comet breaks apart, it seeds its orbital path with debris, and if that path intersects Earth's orbit, we've created a new potential threat that will recur every time Earth passes through that region of space. Now, think about Atlas. It disintegrated relatively close to the Sun, at about 0.08 astronomical units. The debris from that disintegration is now spread out along Atlas's orbit. Will any of that debris pose a threat to Earth? Probably not. Atlas's orbit was such that it likely doesn't intersect Earth's orbit. But we need to track the debris to be sure. And even if this particular debris stream is harmless, the general principle stands. Comet fragmentations create lasting consequences. There's another, even more subtle way that comets affect the solar system. When a comet outgasses, it releases not just dust and vapor, but also organic molecules, complex carbon-based compounds. These molecules spread throughout the inner solar system, carried by solar radiation pressure and the solar wind. Some of them eventually find their way to Earth. Scientists estimate that Earth is constantly being showered with organic material from space, several tons per day of extraterrestrial dust and molecules. Most of this comes from comets. In a very real sense, comets are continuously seeding Earth with the chemical building blocks of life. This has profound implications for the origin of life on Earth. Where did Earth's water come from? Where did the organic molecules that eventually led to the first living organisms come from? Many scientists believe comets played a crucial role. In the early solar system, Earth was probably dry and barren. But over hundreds of millions of years, comet impacts and the slow accumulation of cometary dust delivered water and organics to our planet's surface. Earth became a living world, at least in part, because of comets. So comets are not just threats. They're also life givers, cosmic gardeners that seeded the Earth with the materials necessary for life to emerge. This duality, this Janus-faced nature of comets as both destroyers and creators, is one of the most profound insights to come from modern astronomy. And it raises an interesting question. If comets delivered the building blocks of life to Earth, might they have done the same for other worlds? Could there be life on Mars or Europa, or Enceladus that traces its origin to cometary organics? Could comets be spreading life throughout the galaxy, seeding world after world with the potential for biology? This idea, called panspermia, has been around for over a century, but it's only recently that we've found evidence supporting it. We've discovered that some comets contain amino acids, the building blocks of proteins. We've found that cometary ice contains complex organic molecules. We've learned that comets are much richer in organic chemistry than we ever imagined. So when we study comets, we're not just learning about rocks and ice in space. We're learning about the origin of life itself, about how barren worlds become living ones, about the cosmic processes that might have led to our own existence. Atlas, in fragmenting the way it did, has contributed to this ongoing cosmic process. Its debris will spread through the inner solar system. Some of it will eventually fall into the sun. Some might impact other planets or moons. And some, perhaps, will carry organic molecules to places where they might contribute to future chemistry, future complexity, perhaps even future life. This is the bigger picture that I think we often miss when we focus too narrowly on the technical details. Yes, Atlas is scientifically interesting because it challenges our models. Yes, it's practically important because it affects planetary defense. But it's also philosophically and poetically significant because it reminds us that we're part of a vast cosmic story, that the atoms in our bodies came from stars and were delivered to Earth by comets, that we are literally made of stardust. Carl Sagan famously said, "We are a way for the cosmos to know itself." What he meant is that we, as conscious beings capable of understanding the universe, are the universe becoming self-aware. When you watch this video, when you learn about comets and planetary dynamics and the origin of life, you're participating in that cosmic self-awareness. You're the universe looking at itself and understanding what it sees. That's not just poetic language, it's a literal truth. The atoms that make up your body, the neurons firing in your brain as you process this information, all of that matter was created in the hearts of stars and in supernova explosions billions of years ago. It was scattered through space, gathered into a solar nebula, incorporated into comets and asteroids, and eventually Earth. And now, 4.6 billion years after the solar system formed, that matter has organized itself into a structure complex enough to understand its own origin. That's extraordinary. That's miraculous, even if it's entirely natural. And comets are central to that story. They're time capsules from the birth of the solar system. They delivered water and organics to Earth. They pose threats that force us to develop technology and understanding. They're messengers from the deep cold, reminding us that we live in a dynamic, dangerous, and absolutely awe-inspiring universe. Let me bring this toward a conclusion by addressing the core question we started with. Is Atlas a black swan event? Here's my assessment. Atlas is potentially a black swan, but it's too early to say for certain. It has some of the characteristics. It was unexpected, it challenges our models, and it could have significant implications for planetary defense if it represents a broader pattern of comet behavior we haven't accounted for. But we won't know its full significance for years, maybe decades, as more data comes in, and as we study other comets to see if similar behavior emerges. What I can say with confidence is that Atlas is important. It's a data point that doesn't fit our theories, and those are always the most valuable data points in science. They're the ones that drive progress. Isaac Asimov once said, "The most exciting phrase to hear in science, the one that heralds new discoveries, is not eureka, but that's funny ... Atlas is a that's funny moment. It's weird enough to make scientists scratch their heads and go back to their models and ask, What are we missing? And that question, what are we missing, is perhaps the most important question in all of science. It's the question that leads to revolutions in understanding. It's the question that reveals our blind spots and points the way forward. So regardless of whether Atlas ultimately proves to be transformative, the process of studying it, of grappling with its strangeness, is valuable. It's keeping us humble, keeping us curious, keeping us honest about the limits of our knowledge. And in a field like planetary defense, where overconfidence could be literally fatal, that humility is essential. I want to leave you with a few final thoughts as we wrap up this journey through the science and significance of Comet Atlas. First, the universe is not done surprising us. No matter how much we learn, no matter how sophisticated our models become, reality will always be more complex, more subtle, more strange than we expect. And that's wonderful. It means there's always more to discover, always more to learn. We'll never run out of mysteries. Second, knowledge is power, but only if we act on it. Understanding that comets can behave unpredictably doesn't help us if we don't use that understanding to improve our planetary defense systems, to fund better surveys, to develop deflection technologies. Knowledge has to translate into action to have real-world impact. Third, you matter. Your curiosity matters. Your willingness to engage with complex, difficult topics matters. Science doesn't exist in a vacuum. It exists because societies support it, fund it, value it. Every person who watches videos like this, who thinks about these questions, who cares about understanding the universe, is contributing to the culture that makes scientific progress possible. And fourth, we're living in an absolutely extraordinary time. For the first time in human history, we have the capability to understand our cosmic environment and increasingly to protect ourselves from its dangers. We're transitioning from being passive inhabitants of Earth, hoping we don't get unlucky, to being active managers of our safety. That transition is happening right now in our lifetimes. We're witnessing and participating in something profound. Atlas is a small part of that larger story. It's one comet among countless billions in the solar system. But it's a comet that taught us something, that challenged us, that reminded us we still have much to learn. And in doing so, it's contributed to the long arc of human knowledge and capability. So when you go outside tonight and look up at the stars, remember that somewhere out there, beyond Neptune, beyond Pluto, in the cold darkness of the Oort cloud, there are trillions of comets waiting. Most of them will never come close to the sun. They'll orbit in the darkness for billions more years, perhaps until the sun dies and the solar system ends. But some of them, every so often, get disturbed. They begin the long fall toward the inner solar system. And when they arrive, we'll be watching. We'll study them. We'll learn from them. And we'll be a little bit safer, a little bit wiser, a little bit more capable of navigating the cosmic environment we call home. Thank you for taking this journey with me. Thank you for your curiosity, your attention, your willingness to grapple with difficult questions that don't have easy answers. If you found this valuable, please hit that like button. Subscribe to the channel so you don't miss future deep dives into fascinating topics. And most importantly, share this video with someone you think would appreciate it. The more people who understand and care about these questions, the better our collective chances of navigating the future successfully. Drop a comment telling me what you think. Do you think Atlas is a black swan? What aspect of this story fascinated you most? What questions do you still have? I read all the comments, and your thoughts and questions often inspire future videos. And remember, we're all made of stardust, shaped by cosmic forces, living on a tiny world in a vast universe. But we're also the part of that universe that can understand itself. We're consciousness, awareness, knowledge. And as long as we stay curious, as long as we keep asking questions and seeking answers, there's no limit to what we can achieve. The cosmos is vast and ancient and full of wonders. Comets like Atlas are our teachers, our warnings, are reminders that we're part of something much larger than ourselves. Pay attention to them, learn from them, and maybe, just maybe, they'll help us build a future where humanity not only survives, but thrives among the stars. Until next time, keep looking up, keep questioning, and keep learning. The universe is waiting to be understood, and you're part of the generation that's going to understand it better than any that came before. That's a responsibility and a privilege. Don't waste it. Clear skies, everyone. And may we all be here, still curious, still learning, when the next cosmic surprise comes our way.